The thing that we're trying to figure out is if we water at night, is that more efficient than watering during the day in an urban landscape?
Hey everybody, I'm Candace Shively with Utah State University Extension and the Center for Water Efficient Landscaping, and you are watching our Water Well with CWEL webinar series.
Today we're going to talk about taking a closer look at the efficiency of day versus night irrigation in an urban landscape. So the thing that we're trying to figure out is if we water at night, is that more efficient than watering during the day? And this is an extremely exciting question. I'm going to get into that a little bit here as we go ahead. But if it weren't for the 3 water conservancy districts mentioned here on the title slide, we wouldn't be asking this question. But it was really these stakeholders who came to us asking the question, and I'll share a little bit about why. So I'd like to thank our funding sources, USU Extension, and these 3 water conservancy districts for funding this study and working so closely with us. I also want to introduce my graduate student, Samiksha Pai-Karel, Sammy. Sammy is the grad student on this project who is doing such hard work, and I couldn't be more proud of her. So she's fortunately on the call with us today. She maybe can help me out if we get some tough questions, but otherwise we should just have a bunch of fun. So I want to introduce my lab to start with. There's a lot of people behind this research, and you'll see very shortly that there were many measurements that we were collecting in the field. So this is the USU Small Farms Lab. It's a socially distanced lab picture from back in May. And so here's Sammy, here's me. We had a great group of undergraduates, and then here's another one of my graduate students. And so I want to acknowledge them for their hard work. Every time I look at this picture, I think it looks like an album cover or something fun like that. A little bit about me. I'm a soil scientist. I've worked in both large-scale ag with manure management and corn silage, and also small-scale ag, such as community gardens in urban environments. Here in Utah, as our urban and small farm specialist, I'm focusing on high-value crop production and resource use efficiency. So cut flowers are new to our state, but it's one of the highest value crops you can grow, which is fantastic for our urban farms that don't have a lot of space. Some of our early economic analysis has been that you can make about $2.50 per square foot growing cut flowers. So that's part of my research, is developing that as a crop for Utah, but then also how do we do so in an environmentally conscious way? So looking at resource use efficiency, whether that's water, which we'll discuss in this presentation, or fertilizer, and so forth. I have to admit to you, I'm also a soil physicist. So that means that I really love sensors and instrumentation and equations, but I promise this presentation won't have any equations. But I will show you some numbers. Numbers are the language of nature, and I will show you some graphs so we can actually see how plants are responding to the environment and different things that are happening when we test this very big question. Here is Sammy, the graduate student on the project, hard at work, controlling all of those sensors in the field and taking measurements, and she had some help from our undergrads too in setting that up and taking measurements. So we'll get into all of this here, but I want to acknowledge her too. Okay, so the background on the project. Those of you living in Utah know that we are in a semi-arid state. It's pretty dry here, very dry depending on where you live in the state, and we're growing rapidly. Our population is expected to double by 2060. And we also use a lot of water per capita here in the US. Through different surveys of Utahns, in general, the public supports water conservation efforts. There's a lot of support for that. But they generally aren't interested in reducing the size of their yards, eliminating grass and other vegetation, or investing in drip irrigation. And so because of that, when we're thinking about water conservation, these are just kind of things to keep in mind in terms of what will the public actually adopt and so forth. So we've got a limited amount of water, a growing population, and it's not a problem that's going to go away, especially as we look long term, and models are forecasting that we will actually see some decreases in our water resources as temperatures increase. So we have a little bit of a water problem. And so Let's take a look at where all that water is going. As you can see here, the majority of it is going toward residential. So this is looking at secondary water consumption. And so it's residential that I really want to hone in on today. I love this graph. It looks at where the hourly uses of, or when the usage peaks here during a day. So here, this is looking at 0, so that's midnight until 23 o'clock or 11 p.m. So each hour of the day, millions of gallons of water, and where that's going in the residential sector. And then each of these lines represents a different month, April through October. I colored them in kind of a rainbow pattern. So as we get into orange and red, we're getting into September, October. So you can see that in April and October, our water use is rather low. You're not seeing differences during the day versus night in terms of consumption. But you can see during the growing season, so May through September, that the peak is really happening here between 4 and 8 p.m. or 4 and 8 a.m. Okay, so you can see that there's this heavy water use that's taking place early in the morning. And then if you were to look here later in the day, between 12 p.m., so noon and maybe 6 p.m., that's when we have the least amount of water use. Okay, so peak use is occurring from 4 a.m. to 8 a.m. And the reason for this is because sprinkler irrigation, so I'm not talking about drip irrigation here, but sprinkler irrigation at night is a conservation strategy that we have. So drip irrigation is very efficient. It's about 95% efficient. So we're really not looking at that from day versus night standpoint. We're really just focusing here on sprinkler irrigation. And the reason why sprinkler irrigation at night is considered to be more efficient is because there's different environmental conditions. The fancy word for that is microclimate, that are happening at night that are thought to reduce water losses. These include cooler air temperatures. There's no solar radiation, right? So there's not that bright shining sun beating down on us that can evaporate water. There's also a high relative humidity, and there's generally less wind. So at night it's cooler, there's more humidity, and actually if you picture it, during the day we really heat up, and then at night it cools, and so the coldest time of day is actually right before sunrise, and that's also when we have the most humidity in our air. So it makes sense that that's when the peak water use would be. I like to use the analogy of drying clothes on a line. If it's July and I put my clothes on the line at 12 p.m., they're definitely dry by about 2 p.m. Whereas if I put them on the line, I don't know, at 5 a.m., they might take a little bit longer to dry. And it's because of all of these reasons, right? Cooler at night, no sun beating down on it, etc. So kind of you can think of it the same way in terms of irrigating crops in thinking about these microclimate conditions. Now, as our population grows, however, what the water districts are running into is that the demand now exceeds capacity, right? So if everybody's watering at this time and nobody's watering at this time, that's some serious stress on our systems, right? There's only so much capacity for everybody to be watering at night. And so the question really becomes, how much water are we actually saving? Is it worth it as a conservation strategy to keep this going? In that case, there's going to be a lot of engineering that needs to be done to increase capacity. Or how bad would it be if we spread it out across a 24-hour period, if people were watering during the day too? So that's the reasoning behind this study. That's why we're doing the research. So let's picture this a little bit more. This is a picture of our plots. These are zinnias. I'm going to get into that a lot more coming up here. And you can see in this picture that there's some sprinklers going off in the background, right? So when we think about all the places the water can go, well, the very first thing is there's some irrigation that's happening, and it's hopefully going down to our plots or down to our plants at least, right? Some of that water is going to make it to the plants. If we're lucky, most of that is going to go into the soil, or I should say our goal is for most of that to make it into the soil. Now, if we're very water-wise, when we're irrigating just enough that we're wetting the root zone, right? So that there's water, it goes into the soil, into the root zone, and that's it. If we add a lot of extra water, it's actually going to drain past the root zone. So it'll go deep in the soil where the roots are, and that's inefficient, okay? So our goal here when we're testing is to water just enough that it stays in the root zone. It's not going beyond that. That would be deep drainage. So one place the water can go is down. That's into the soil. Another place the water could go is it could run off. So if we're putting a bunch of water on at a time, it can start to pond on the surface, and instead of infiltrating, it'll just start to run off the surface. Now, this isn't a big issue in Utah in the middle of summer when we're irrigating with sprinklers. This is an issue in the spring when our snow is melting, but that's for another talk. As far as we're concerned here, we can kind of disregard runoff as something that we don't have to worry about too much when we're tracking all of the places water goes to see if there's differences in day and night. Another thing though that can happen is wind drift. So the idea here is that water is coming out of the sprinkler, right? It's going into the air. There's all of these water droplets. Some of it's going to make it down, but perhaps the wind just takes some of it away. It evaporates it right away. It takes it off to another place. That's something that we don't want to happen. And that's a criticism of daytime irrigation, is that typically our wind speed is greater during the day, so we could lose more water due to wind drift, potentially. We'll see. Then the last direction I want to look at, so we've gone down to the side, and now up, is evapotranspiration. This is also referred to as ET. And so ET is looking at evaporation from the soil surface and also transpiration from the plants. So during the day when the sun is shining, the plants are doing photosynthesis, they're taking in CO2 and making energy for themselves. But when they do that, they're releasing water vapor. And so that's a really complex subject. I'm guessing a lot of you have heard that term before. If you haven't, it's an awesome topic that we could maybe talk about another time. So just take me at my word from here. But when there's ET, that is actually in response to the temperature and the humidity outside. So the higher the temperature, the more ET. The more dry the air is, the more ET. So if we think back to those conditions of day versus night, during the day it could be hotter, it could be less humid, and that could create more ET. So let's see, our goal here now is to measure then these different processes and see if they're different during day and night. And so this should tell us not only what's happening if there's a difference, but it'll also tell us why. And that's gonna help us relate our findings beyond just Logan, Utah. Okay, so by the way, you are all now soil physicists, because this is called a water balance. So we're doing a water balance approach. We're looking at all these different places that water can go. That's all it is. So when the water districts came to USU and said, how much water are we actually saving? Our first thing to do is to go to the literature. What have other scientists said? What have they found out? And we really thought that this would be clear in the literature, to be honest. But as we looked into it, we found that the studies were mixed. The results were mixed, to put it mildly. One of the challenges with the studies is that they were tested outside the US. They looked at large scale ag systems like cornfields, so not urban landscapes. And they also were in low elevation environments. And we're at high elevation here. The sun is bright and intense. So there's some differences between the locations. And what they found, there's three main studies that looked into it. They found that those wind drift and evaporative losses were 7 to 17% greater during the day than at night. Okay, that's the range across the studies. So saying that, yeah, night looks to be more efficient, but it varied by how much. However, another study came along and said, yeah, but what about the microclimate? Or the conditions out there. So if you are watering in the heat of the day, right, it's hot out, that irrigation water is a bit cooler in temperature. So if we're in the 90s, that irrigation water could be in the 50s or 60s. So if we're irrigating during the hottest part of the day when the plant needs the water the most, we could actually be cooling the air temperature. And when we're watering, we're putting water into the air, we could actually be increasing humidity. And then in that case, daytime irrigation could be more efficient. So there's a lot of controversy. I shouldn't say controversy. There's a lot of discussion in the literature, and there's not full agreement among scientists. And so, so that was very interesting to find. So, and the question now becomes, well, what about what's happening in Utah, where we're at high elevation? What's happening with urban crops, turf being our #1 urban crop? And what if we test all these factors together? So what if we're not only looking at wind drift and only looking at ET or only looking at microclimate? What if we measure everything? Now, the reason these other studies didn't do that is not because they're bad studies. They didn't, it's just a whole lot of work, and it's really expensive to do. And so we're really lucky to live here in Utah and have such amazing relationships between our state and our water conservancy districts in USU that we're actually able to do this. And we have Sammy, who's willing to be out there controlling hundreds of instruments. So these are the questions that we had. We decided to test 2 types of urban crops. The first one is turf grass, because that is most important to our stakeholders. That's the main crop that's watered by sprinklers. And then the other one we chose to test is the zinnia. Zinnias are a very common flower in the garden, so people just like to grow them. They're easy to grow. They're also a little bit drought tolerant, actually. And they're also a common cut flower to grow as a crop and sell. Each zinnia, you can get about $1 per stem per flower. Not bad. The thing that's neat though, so we're testing 2 crops that look very different. If you will, they have a very different plant architecture. So turf, for example, is made up of all these thin, tiny leaves. We keep ours mowed at about a 3-inch height. There's pretty homogeneous coverage over the surface. There's some weeds in there, you can see, but it's short growing. It's pretty consistent in its coverage. It's a perennial, so it's planted. It's there in the beginning of the year, unlike zinnia, where we've got bare soil to start with, and then it grows and has these broad leaves. It gets to be about 3 feet tall. So really different. So maybe their water use is going to be different. Maybe water is going to land on them differently. I don't know, but we're going to test them both to see how this holds up. So the goals of this study are twofold. The first one is what we've been talking about. We wanted to know if there's a difference in efficiency by looking at both the microclimate conditions, so what's happening with air temperature and humidity, but then also looking at ET or evapotranspiration and wind drift, those kind of things. How are those processes different, or how are they the same with these 2 crops? But we didn't want to stop there. So if we're ever testing a practice, it's also important to know how that plays out with the plant itself. What does yield look like? What does quality look like? If one is better for the environment, but you end up having yellow grass, I don't know, people might not want to adopt that. So we, or conversely, maybe one's less efficient, so the turf grass grows, takes longer to grow, and I don't have to mow as often. I don't know. So these are things that we wanted to take a look at, is both what's happening with the water and then what's happening with the plants too. So this study got established in 2019. It's at our Greenville research station in North Logan, Utah. And so you can see here, it's nestled into a very nice urban environment that's becoming even more urban. Here's our field site. It's a large area. And so we'll kind of zoom in. This is an old picture of the field before we did a little bit of rehabbing of it. So it looks a little bit better than this, but gets the point across. So here, these black dots represent sprinklers, and they are spaced 50 feet apart. It's an in-ground sprinkler system. And then we have, and so they're in zones. So certain sprinklers are connected together, which means we control each zone at a time. And then what we did is in the center of each of the 4 sprinklers, that's where we nestled our plots. So we have 12 plots. Each plot is about 16 feet wide and 16 feet long. And the green colors represent turf plots, and the pink colors represent zinnia plots. Those plots that have a darker color, so dark green or dark pink, that means they're being watered at night. And then the light colors mean that they're being watered during the day. Okay, so 12 plots, and we're looking at 2 types of crops and 2 irrigation times. Just to look a little bit up close here, so here's a turf plot, for example. This is what it would look like here in the field. And similarly, here's a zinnia plot right before it got planted. There's some landscape fabric here in between the rows, and then the rows were planted. Okay, so our irrigation, we watered 3 times per week. At night, we watered from 2 to 4:30 a.m. and during the day from 2 p.m. to 4:30 p.m. So the thinking here is that, you know, in the summer, the sun rises pretty early. So this is getting as close to sunrise as we can. And then in the day, this is really the heat of the day. They're exactly 12 hours apart. And kind of this is just for your information, we can control each zone at a time. So I think each pair of plots was watered for about 45 minutes, maybe 50 minutes. So at 2 a.m., maybe 2 a.m., maybe this one gets irrigated. Then at 2:45 or 2:50, this one gets irrigated, and so forth. And then we randomized that. And we applied 0.4 inches each time. That was just according to recommendations. I think it's 80% of ET, which is the recommended amount. So the plants are maybe a little bit water stressed, but it's per recommendation. So here are all the things we measured. Remember I said we want to track everywhere the water is going so that we can have good measurements of this. So fortunately for us, the USU weather station, one of them is located right in our field, and that weather station measures rainfall for us. We're also tracking that. Then with our sprinkler system, we can control what time the water is applied and how, and by that we can calculate by how much, but there can be differences from day to day. There's differences in pressure. There can be sprinkler issues and so forth. So we also installed these flow meters into the sprinkler system so that we could track exactly how much water is going to the plots each irrigation event. We've got a really good number on what's coming out. Then we've got catch cups here, and the catch cups tell us, well, we know how much is coming out of the sprinkler from the flow meters. The catch cups tell us how much actually makes it to the ground. So in the turf, that's really easy. We just put the catch cups on the ground. There's 9 per plot, and so 6 turf plots, that's 54 catch cups that we're analyzing. Zinnia are a little bit trickier, especially as the season progresses, because they get big and their canopy closes. So we actually have 2 sets of catch cups. There's 18 per plot times 6 plots, which is 108. So this top one here is positioned at the canopy top or a little bit above it. And its job is to collect water that, you know, it makes it through the sprinkler, goes through the air, hits the plot. But then the lower one tells us if some of that water got intercepted by the canopy. Some of those drops hit the leaves and then they evaporated, or they didn't make it to the ground. But really these catch cups are helping us understand what is actually getting into the soil. And then in the soil, we have soil moisture sensors that tell us how wet the soil is. We've got some really precise ones here near the surface in the root zone. And then we also have another one that's very big. It goes, I think, 3.5 feet deep. And this helps us make sure that there's no deep drainage taking place. Because remember, we want to keep it in the root zone. Every plot is instrumented. Then we also looked at measuring the microclimate conditions. So again, we're very thankful for this weather station. It's telling us what the wind speed is. It's also telling us what our typical air temperature is. We have a fancy sensor that tells us the surface temperature. So how hot is this canopy, or how hot is the soil? And then we have even more sensors that look at the air temperature near the canopy, as well as the humidity. Here it is in the zinnia plot. It's kind of nestled in there. It's right in the middle of the canopy. What's that temperature of the canopy and what's the humidity of it? So we can see if it changes with irrigation. And then there's a bunch of other instrumentation to do other things too. Here's Sammy installing some net radiometers, but we won't get into that for today. Then I feel like we just got through all these sensors. Here's a fun thing. We also looked at measuring yield and quality. So mowing the turf, as needed. It depended on the month. So October, we only had to mow once, but in June and July, it was twice a month. We saved all the clippings that we cut, and so that we could measure their weight to see if there were any differences in productivity. Maybe the grass is growing more slowly with day irrigation, for example. We wanted to find that out. And then we also took pictures once per week so that Sammy could analyze the percent coverage of the turf and its greenness as well. So those are just ways to look at the quality. And then for the zinnia, we harvested 1 to 3 times per week, depending on the time of the season. And we looked at a lot of things. So we counted the number of stems that were harvested each day. And then within that, we graded them. So the ones that were good enough to sell to florists, really high quality flowers, those are called marketables. And if they weren't, they were called culls. And so the idea here is that if one of the irrigation times is more efficient, maybe it's producing more zinnias, but is it doing so in a meaningful way? Or is it just producing more culls? I don't know. So those are all of the measurements. And so now, let's see, I want to share a little bit about our findings. So we're close to a half hour here. I guess I'm going a little bit, some over. I just want to say though that these results are not even hot on the press. They're about a year off from being on the press. So these are ones that we're working through. It's very, very preliminary, but I think they're fun to look at to just kind of get an idea of how things are shaping up, but they're not our final answer. Hopefully we can come back and share the final results here at the end of the year, especially as we have 2021 to test, because there's differences from year to year. I'm going to share our 2020 results since we have a full season of that. So let's recall that there's all these different places that the water can go, right? And so the first one I want to focus on is wind drift. And remember, the thought is that wind speed is greater in the day than at night. So let's see. Okay, so I zoomed in on 1 week. It's just a random week in August to kind of take a look. So there's the date on the bottom here, starting on the 10th, ends on the 17th. The place where the tick mark is, that's midnight, and then this tick mark in between the two, this would be noon. And we're looking at wind speed in miles per hour. So first off, you can see that in the beginning of the week and the end of the week, it really wasn't very windy. But in the middle of the week, we had some serious wind. So you can see here that on the 12th, for example, it's midnight right here, and this would be our early morning. The wind speed is pretty low, and then afternoon, it got to be about 8 miles per hour. Still not that high, but certainly higher than at night. So you can see that there's this difference here, and the same thing happened on these days. So in general, that's true that the wind speed is greater in the afternoon, but certainly not always. So percent wide L, this is the percent of wind drift and evaporative losses. I'll explain that a little bit more, but these bar charts match up with the dates. So on the 10th, we irrigated, and the black bar is turf that is watered at night, how much water was lost to wind drift and evaporation. And the green is turf that's watered during the day. Dark purple is zinnia watered at night. Light purple is zinnia watered during the day. And so first off, on the two ends of the week where the wind speed is lower, you can see that there's not such differences, but even on days when there's not a lot of wind, we're losing about 30% of our irrigation water to wind drift. 30%, that's a lot. Even on days when it's not that windy, night or day. But you can see there are some trends here where day is losing more due to wind drift. Now, on the days when there's a lot more wind speed or a lot greater wind speed, that's when we see a bigger difference. So here it goes from around 30% to 45%, and then in the zinnia, it actually makes it up to 55%. More than half of the water was lost to wind drift on this day because of the wind speed. So certainly there can be differences between night and day as a function of wind speed. Okay. But let's kind of add that up now and look at it across the season. So this is looking at the average percent of water that is lost through wind drift in June, July, August, September, and October. So for each of these treatments, they're the same as what were in the other slide. Oh, I guess they're a little bit different, I'm sorry. Dark means night and light means day. So turf is in green and purple is zinnia. And so you can see that there are differences. There's also a lot of error. So there's a lot of variability around it. So if we average all of our plots, these are our general trends. There's a lot of noise in those numbers. And then if we look at it, if we take the average of all of these bars across the season and look at turf and zinnia, night irrigation versus day irrigation, you can see that indeed day irrigation is losing more water to wind drift than night, but the differences are rather close, right? 2% more in turf and 6% more in zinnia. Okay, now I want to talk about ET, or evapotranspiration. And remember, this is thinking about evaporation from the soil surface and transpiration from the plants, and it's a response to the air temperature and the humidity. So the hotter it is, the more ET, and the drier the air is, the more ET. If it's more humid, there's less ET. If it's cooler, there's less ET. So we want to understand how that microclimate, or how those conditions look. Okay, I know these look a bit busy, but bear with me. They'll all have the kind of the same format going forward. So again, I picked a random week in August. They all follow this trend, just to kind of zoom in and see what these trends are. It's really neat to see how nature is responding to what we're doing. So we start on August 23rd, that's a Sunday. The graph goes until Saturday here, August 29th. And what we're looking at is the canopy air temperature. So we have those sensors that are right on top of the turf grass and right in the canopy of the zinnia. And so these are the results. Now we averaged them across plots, and so we're just looking at the averages here. Now I mentioned we water 3 times per week, every Monday, Wednesday, and Friday. So that's what I've denoted here. These lines represent days that we irrigate. Now each tick mark, so there's a tick mark here that says August 24th. This is midnight. So halfway between the ticks, that would be noon. And so on top here we have turf. Black is irrigated at night. Green is the canopy temperature of turf that's irrigated during the day. And then down here is zinnia. The darker color is a night irrigation. Orange color is a day irrigation. So here's our canopy temperature. This is our irrigation day. For our nighttime irrigation, that would be happening right around this time period, right? 2 to 4 a.m. And you can see in the turf that black line is slightly beneath the green line. Not even a degree difference, but it is a little bit lower in temperature. So just by irrigating, we're decreasing the temperature. You can see that a lot more in the zinnia, that nighttime, the temperature of the canopy of the plants that are watered at night is lower by a couple degrees here. And you can see that, so we irrigated right here. And you can see that lower temperature actually holds for a good 12 hours. It keeps it cooler. But over here, now this time, we're in the afternoon. This is when we irrigated during the day. So you can see that when we irrigated, here they were following each other pretty closely, the temperatures. We irrigate and boom, that canopy temperature from day irrigation drops. I mean, and that's a big drop in temperature here, right? That looks to be about 8 degrees or so. It's less pronounced in the turf, but there is a difference. We're reducing the temperature, which again, that one scientist early on said, you might be reducing the temperature when it's the most stressful for plants, and that could actually help ET, could make it lower. Okay, so this is when we're irrigating. Now here's the next day, the 25th. We didn't even irrigate this day, and you can see that the nighttime, the plants that get irrigated at night are hotter. They're warmer by a few degrees, even less in turf, but there's a difference. I don't want to get into this too much, but what we're thinking is that the plant is stressed out. The ones that are getting irrigated at night are stressed, so their temperature is higher, and there's this legacy effect happening, even on days when we're not irrigating. Now here we are, it's Wednesday, we irrigate again, same thing is happening. It's Friday, irrigate again, same thing is happening. So we are seeing that when you irrigate during the day, it reduces the temperature a lot more than as you are at night. These graphs are the same thing, turf day, night, zinnia day, night, same week, start on Sunday, end on Saturday. But now we're looking at relative humidity. How much humidity is in that air? The first thing I want to point out is that, let's see here, again, we irrigate every Monday, Wednesday, and Friday. And so you can see here, let's see. All right, so here's midnight. I think it's easy to point out here in the zinnia, but you can see that the relative humidity of the zinnia that are watered at night, you can see that their humidity goes up to 100%. There's a good 10% difference in humidity here from that night irrigation, and it lasts. But then here's our daytime irrigation. Okay, so that looks to be about 45% humidity. We irrigate and boom, it's almost at 70%. So quite a difference that's happening from that daytime irrigation. Here's our next irrigation date. You can see that the irrigation increases from night, and then it also increases when we're irrigating during the day. And so the question that we're asking here is that we're really thinking about ET. ET doesn't happen so much at night. The plants don't transpire at night for the most part. It's when the sun is shining, they're doing photosynthesis, that's when they're losing water. So we're not really concerned about plants and how this influences ET at night, but this is very interesting about what's happening during the day. It's making the air more humid, which could reduce ET, but we'll see in the next slide here. All I wanted to get across is that when you water, the air around the plants has an increase in humidity. Now, this is not necessarily true with drip irrigation, but it is for sprinkler irrigation. All right, now evapotranspiration, we're kind of putting it together. Same graph, we're looking at Sunday through Saturday. In August, we're looking at ET, inches per hour. Don't worry about these numbers, they look really small. I'll show you what they are as we add them up across each month and then the season, and then they'll look a little bit more normal. I just want you to take a look at what these lines are doing. So we irrigate Monday, Wednesday, Friday, and so let's see here. So now we've got the 24th, this is midnight, this would be noon right here, and then here's the next day. So, so we water at night sometime in here. There's no ET taking place. It's essentially zero because, again, it's dark out. The plant isn't doing ET. You can see that the peak time of ET is occurring in the afternoon when it's the hottest, right? It's the hottest in the day between noon and 4 p.m. That's when we have our peak ET. There's not a big difference in ET though. So you can kind of see that that black line looks a little bit higher up than the green line. And similarly here in the zinnia, the black line, the ET from the zinnia that are irrigated at night is a little bit greater than what's happening during the day. It's brought down a little bit from irrigating. But the interesting thing that I did not expect is that it's not on the day of irrigation. It's actually the next day that we're seeing continued differences in ET. So here at this peak time of ET, when it's the hottest, the plant is transpiring as much as possible. You can think of it kind of sweating to keep itself cool in a way, not completely, but kind of an analogy, that there's more ET happening from the night irrigated ones. Again, because we think that they're more stressed. And that's getting back to this idea of when we're applying water. If we're applying it during the day when the plant is using it and needing it, it's kind of pointing that that could be more efficient. If we're looking at this piece of the puzzle, remember we've got the whole wind drift thing to think about too. So if we add up the amount of ET, we were looking at it hourly, but say we added up across an entire month and season, looking at it June through September, we're still working on our numbers in May and October. So if we just look at these 4 months, these are turf, zinnia. So turf that are irrigated at night, what's their ET? Turf irrigated during the day, and then zinnia night, zinnia day. You can see that the numbers are really close, right? Overall, they're really close. And when we add them up, there's a little bit more ET happening from the night irrigation, 0.2 inches. If we look at it from the zinnia, it's a different number, but it's holding the same pattern. So it's 0.3 inches more ET from the zinnia that are irrigated at night. Okay, so we looked at wind drift and we said that there's more wind drift from daytime irrigation. Then we talked about ET and we said there's more ET from nighttime irrigation, but none of these, we haven't tested these statistically yet. That's coming. And I am not a betting woman, but if I were to, I would say they're probably not going to be significantly different. And it looks like these, I like to think of these two processes as competing against one another and essentially canceling each other out. So far, at least what we're seeing. All right, so we made it through all of my mumbo jumbo about physics and where the water is going. Thank you so much for sticking with me. Now I want to talk about the yield and the quality data. So in terms of collecting the grass clippings and measuring them, I think this must be a wet weight. There's not a difference in how much biomass is being produced by the grass. So no, I don't, there is not a difference in how frequent we have to mow for day versus night irrigation. It's the same amount of productivity. If we look at quality ratings, now we're still working on these. The early numbers that we have are looking at percent cover. So we've got the month here and then the night irrigated turf versus day. And you can see that 97, 99% coverage, it's really high. It goes down as the season progresses and it gets water stress. But they're pretty close numbers. The night might have a little bit less coverage. DGCI is a measure of greenness, and 0.37 is considered good for a Kentucky bluegrass. So you can see that we're at that number of 0.37 or above. So there's really not a difference in aesthetics from this standpoint, but there are other visual indicators that we need to look at. So that's in process right now. But overall, it's not looking like there's a large difference between the two. If we look at the zinnia yields and quality, so here's looking at total yield. How many total stems did we harvest? Our harvest season begins at the end of July and it goes through October or the first hard freeze. And the blue line is night irrigated, orange line is day irrigated, and you can see that there's a little bit of a difference. By the end of the season, we're averaging 12 zinnias per square foot compared to 11 with day irrigation. But if we look at the quality of those flowers, we're at about 2.1 zinnias per square foot, or 18% of the zinnias are actually marketable. For day irrigation, that number is 2.5 or 23%. Okay, so again, not big differences there either. Probably won't be significant. All right, so that's most of what I have to share with you today. The next steps that we'll be doing are our continued analysis. Sammy's working to refine our ET calculations even further. And so that's exciting. We're also preparing for one more year of measurements. 2019 was an interesting year. We only have about a good half season of data because that was the year we installed. It was also really wet in the late spring, early summer period. 2020 was our first full monitoring season, and so 21 will be a great test to see differences in year-to-year variability, just because weather is different every year. And an exciting thing that'll be coming out of this is that we'll be able to develop irrigation recommendations for cut flower crops. So starting with the zinnia, and then after this study, we'll probably be putting in different cut flowers to figure out those recommendations, since we can do that with all the instrumentation that we have out there. So those are our next steps. In summary, understanding water conservation with day versus night irrigation strategy is complex. There's lots of instruments and calculations, and so we're trying our best to be thorough and really look at it from every angle. Wind drift losses tend to be greater from day irrigation, and ET tends to be greater from night irrigation. And these two processes seem to cancel out to make there not be such a difference between the two timings. And we really didn't see differences in quality or yield of the urban crops that we tested. So with that, thank you all so much for listening. I'm excited to answer questions here if you have any. And I really want to thank all of the people behind this project. Of course, Sammy, but also our funding organizations, USU Extension and Weber Basin Water Conservancy District, Central Utah, and Jordan Valley. And then there are also a lot of folks here at USU involved behind the scenes on the research too. So Dr. Neil Allen, our irrigation engineer, Paul Harris, Scott Jones, Larry Rupp, and Kelly Kopp. So with that, I'll stop yapping and I'm happy to take questions.
Great.